Okay. So, today I'll be talking about sorting algorithms and greedy algorithms. Okay, so as of right now, so first of all, sorting, pretty sure you guys already know what sorting is. It's just like ordering things in a specific way. So as of right now, the most efficient sorting algorithm is n log n. So remember, log n means base 2, not base 10. Sorry. So there's sorry. So so okay, sorry about that. So there's a lot of different sorting methods right now that are n log n. I won't be going over them because you don't really need to know them for bronze. I feel like in general you don't really need to know sorting for bronze either. It's mainly just for convenience. But there is one type of sorting which I'll go over because I think it's interesting, and the idea of it you'll see more later. So, yeah. As for how to sort an array, you can just use the standard library sort because it's already n log n for C++. So yeah, here's like an example of that. Make sure to remember to include algorithm if you're going to use sort. Okay. So the specific type of sorting I was talking about is merge sort. So basically the idea behind merge sort is that you're going to take an array and then you split it into two equal lengths. And what you do is you sort each half essentially by calling itself with each half. So then once you've sorted each half, all you have to do is just merge the two sorted arrays into one array. Yeah, so an example I can show here is, so if we were going to do merge sort on, like, for example, this array, so what we do is we first split it into half, right? And then we'll take a look at this half first. So when we're considering this half, we're just going to keep splitting it down in half. So we split this in half, and then we look at this segment, and then we split in half again, and then we look at this segment, right? So this segment's already sorted, right? Because it's just one value. So then we look at this segment. And when we look at this segment's also sorted, so we also just return this back up. So now we look at this entire segment. So in order to sort this entire segment, we can already see here it's already sorted, so we don't have to do anything, so we just return back up to here. And so now we do the exact same thing what we did over here on this side over here. So we're going to split it again, and then each half is sorted. But when we start merging them, we notice that this isn't sorted, right? So we have to swap them. So what we end up returning here is actually 2, 4. Back up to here, like to this division. So now we have this, right? We have two halves. We have this half and we have this half. So the way we merge these is we keep an index here, and we keep an index here. This is a 2, by the way. And then we compare the values at each index. So we see here that this one is actually less than this one. So we add this. And then we move this pointer over here. So then we compare this with this pointer. And then we see that this is 2, which is less than 8. So we push this one onto our answer. And then again, we move this pointer over here. And we compare again. We see 4 is less than 8. And now this pointer is like pointing to nothing, so we just add 8. So does like that merging make sense? Like, do you guys like understand like what just happened, basically? Like how we went from this to this. Two twos. Okay, so let's say this was a 2 here instead. Then basically we're just gonna keep splitting it, right? So when we get to like when we're considering this segment and we split this segment into 2, we see that both halves are already sorted. And then when we merge them, we see that they're we're gonna have a pointer here and a pointer here, right? Or not really a pointer, but just like an index, right? So we're gonna look at this value and we're gonna look at this value here. And we're gonna see they're both 2, so we end up just pushing both of them. And then if we go back to here, for example, like this step, when we're merging this entire segment over here, it's pretty much like what I just said. So we have an index, so we consider this value, and we consider this value in each half, because this is like a recursive function. So we can like get back this sorted half, and we can get back this sorted half as well. So yeah, we just like do the comparing thing. So first we push in 1, then we move then we consider the next value in the left half. Then we see the right half is less than this, or the value in the right half. So we add 2, and then we consider the next element, and then we compare this and this. So we end up with 2 over here. Does that make sense? Like, do you guys get how like this like is sorted? Because like essentially we have like a recursive function, and so we're given an entire array, and then like our function will take in an array, and then it's gonna sort it. So what we can do is we can just consider the first half of the elements, and then we call our function on the first half. So we get the first half sorted. And then we can also call it on the second half, so we get the second half sorted. So now we have 2 sorted arrays, and we're just trying to merge them and return it. How do we do that? We just compare values, and then we move the index of the one that has the smaller value to keep comparing. So basically what I explained here. So if that's, so does that like, yeah, okay. I'm gonna assume you guys understand. If not, you can like ask me. Okay, so that's this half, right? But we still need to do this half. This half is already sorted, so the process is still the same. A small recap. Okay, yeah. So, essentially, okay. Let me erase these markings. So, basically, the whole idea of merge sort is that we split our array and then we merge 2 sorted arrays. So when we're given the entire array, first we split in half, right? Then we look at the left half. Then we do this process again on the left half. So we look at this part and then we split it, and then we look at its left part. And then we just keep doing that until we get down to 1 element. Then we return this back up because it's like a recursive function. And so once you return this back up, we also look at the right child, right? The right child's also going to return something. So we have 2, so now we have 1 and 8. And so we basically merge them. And how do we merge them? Well, we merge them by having like indices pointing at certain values. So initially, like when we have 1, 8 and 2, 2, 2, then we have one index for the left one and one index for the right one. And whichever one has a smaller value, so in this case, this one does, then we increment this index. So I becomes 1. So it'll point at this value. And we just keep doing that until we get this. And this in turn will return back up to this part. And then the other half will also be sorted, and then we'll restart like the merging process. Do you get it? Okay. So now in terms of complexity, like how long will this take? So we know we have n elements, right? So this looks a lot like a rectangle, or like just a 2D array, right? Because we have n values here, and then now we just want to know like how many what's the depth of this basically. So if you remember yesterday when I was explaining, I forgot what I was explaining, but like essentially each time we divide it in half, if we do this process backwards and instead we're like merging each half, then we can see the size of each segment will keep doubling. So let's say this is x, right? So then this, like if we consider this segment's going to merge with another segment of equal length. And then this segment in turn will merge with another segment of equal length. And this segment will merge with another segment of equal length. So essentially, we're going to keep doubling x times. Which means that x is just log of n. And so we know the depth is log of n. And we know the width part is like O of n. So the total complexity will be n log n. Does that make sense? Honestly, it's like fine if you don't really get it. I just like kind of want to introduce this idea of like splitting our array in half and then working on one half, working on the other half, and then merging it. And just like continue doing this down. Because you'll see this a lot later on. This idea is called divide and conquer, which you won't need to know for bronze, but I think it's like good to introduce it now. So do you guys have like any like questions, like overall? Okay. Yeah. So you won't really need to implement this. Like I said before, you can just use the built-in std sort function, which also runs in n log n time, using like some other type of sorting algorithm. Okay, so a practice problem for sorting. It's not really like for sorting specifically, but it uses sorting as like the algorithm. So yeah, I'll give you guys a couple minutes to think about it. You guys don't have to come up with like the full solution right away. So just any ideas aren't good. Uh, yeah, yeah. So, but then what do we do for the individual kayaks? Actually, first of all, I should ask, does this problem statement make sense? Because the first time I read through this, it was like a little weird. Okay. Um, but yeah, we can sort the weights and take consecutive differences. But what, how do we choose which ones to do for the single kayaks? So for the single kayaks, what we can actually do is we can just brute force which ones are going to be single. Because we notice that n's only 50, right? So we take n squared to choose a pair that are like by themselves. And then with the rest of them, we do what yeah, so we just sort the rest and then take consecutive differences. And then we just take the best answer that we find. And if you're like hesitant about why taking consecutive differences is like correct, you can like consider them as like points on a number line. So like let's say we have weight A, weight B, weight C, weight D with like it's increasing. Then essentially what we're asking is like the difference or like the distance between 2 points. How do we like pair them up to minimize them? This is always going to be best because if we do this, we can like already see that we're like this is less optimal because we're covering this part twice as much actually compared to this solution. So yeah. So if we ignore the single kayaks, we can just do adjacent pairs after sorting, and then just iterate over all pairs for the single kayaks. So does this problem make sense? Do you guys have any questions? Okay. Here I have another question. So again, I'll give you guys some time to think about it. So do you guys have any ideas? Okay, so if you guys don't have any ideas, then I can go over after every explosion. Caused by the pre. Okay, so that's one way to do it, but I think implementing that's a lot like harder. I'll go over a much easier way to do it. So first of all, like okay, let's look at this example. First of all, we sort it by hay bales, like by location. So let's say we hit this hay bale, right? So what we can actually do is we can actually consider this explosion as two separate explosions, like explosion chains going in each direction. So let's first look at this direction, right? So we can just keep like a tracker of like our current radius, and basically if this point is within our current radius, then we just go to this point and then we increase our radius, right? Now I think the thing that you were worried about is that once we get here, once this one blows up, you're probably worried that it's gonna like hit some hay bale over here. But if that happens, then that'll actually be covered by the reaction going this way. Do you see that? Because this will only be of r plus 1. Yeah. So the one over here will already be covered by the explosion at distance r from here. So you don't actually need to consider going in both directions for each explosion. Instead, you can just keep going in this direction. So here r is equal to 2. And we see that, yeah, it's not enough to explode this one. So on this side, we only get 1. But if we look at this side on the right-hand side, when we explode this one, our radius is now 2. And notice we don't have to worry about this one, right? Because we already covered it when we went left. So that makes like implementing it a lot easier. And then once we get to here, we see that this 8 is within range. So we go over here, our radius becomes 3. And there's no more, so our answer will be 3. Or sorry, 4, because you also explode this one. Does this make sense? So yes, you could do what you said, but I feel like implementing it that way, there's a lot of details. And during contests, you probably like don't want to figure out those type of details. Like this way would be much, much easier to implement. By like just like basically just iterating through where your starting point is and then going in each direction. Does this make sense? The time complexity. Well, first of all, we notice n is only 100, right? So worst case, what's gonna happen is, okay, so we know we iterate over all of them, right? So when we do that, that's already O of n, right? But notice when, like, for example, this one, we only go in one direction for each of them, right? We don't like go backwards at any point when we're considering this one. So when we're considering this point, we're only going to sweep over every node at most once, right? And so for one point, if we sweep over all the nodes one time, that's O of n, right? And then we do this for every node. So that's O of n square. Which actually fits like very comfortably, if that makes sense. So yeah, so do you get, yeah, okay. Yeah, so the main thing is just to realize that we actually only have to go, we can actually split this explosion into two chains, and for each chain we actually only have to go in one direction, and we can just keep going that way. So yeah. So a recap of this. Yeah, so this is like a simulation problem. We sort the hay bales, and then each explosion will cause two chain reactions going in each direction. So we just calculate for each chain how many hay bales we end up exploding, and then the answer is just the sum. Yeah. Alright, so binary search. So now, strictly speaking, binary search, you won't actually need it until silver. But since we're on the topic of sorting anyways, I think we're going to go over it because binary search is also very useful to know. So yeah, okay. So what does binary search do? So basically, given a sorted array, we want to find the position of some number x. So naively, how would we do that? If like what would your like first instinctive thought be? Use the find function. Well, yeah, pretty much. A for loop and if statement. Yeah, okay. Yeah, those are pretty much all the same. Now the issue with that is that for vectors, at least, the find function is O of n, right? So let's say we had like 10 to the 5 queries, right? And let's say our array size was 10 to the 5. Worst case, our complexity is going to be n squared, or n times the number of queries, which is not good, right? It's going to be too slow. But we're given that the array is sorted, so we should try and exploit this, right? So instead what we do is we choose the middle value. So let's say we're given some values, right? Like 1, 5, 6, 8, 10, 20. Right, so this is our sorted array. So what we do is, let's say there's a 7 here. So what we do is we first check this middle value. And let's say let's say we're trying to find x is equal to 10. So first we look at the middle value, like in the entire array. And we see that 7 is less than 10, right? So what do we know from this? What we actually know is that we don't have to consider any of these values, right? Because all of these values are less than this value. And this value is already less than this value. So we know these are going to be less than this value. So there's no need to check them. It's kind of like how, like, if you guys like use like those dictionaries, like the big ones, and like you're looking for some letter, then like you don't have to like check all the letters before it, kind of. So it's kind of like that. But yeah, so yeah, this is like the whole idea of it. We choose the middle value. So we see that 7 is less than 10. So we know that the answer is going to be somewhere within this range, right? So how do we do that? We just do the exact same thing again on like this segment of the array. So again, we choose the middle value, and coincidentally, this is our answer. Let's say instead we were looking for 8. Then this time we see that 10 is greater than 8, right? Hopefully it is. So what does that tell us? That tells us that this entire like back part we don't need to consider. And we know that we don't need to consider this entire segment either, right? Because of our previous check with the 7. So we know that it's somewhere within here. And in this case, there's only one value. So we found our value. So does this process make sense? Essentially, we're just exploiting the fact that our array is initially sorted. So when we choose some value, if some value is less than our target value, we know all the values before is also going to be less than our target value. And if we know if our current value is greater than, we know all the values to the right of it are also going to be greater than it, greater than our target value. So we don't need to consider them. And so basically like that, we're shrinking our range. And so the way we do that is we have 2 pointers here, like say L and R. And so we choose the middle value M, which is just the average of the two, so L plus R over 2. And then we see that we don't need to consider this segment, so we move L over here. And then this will become M. Again, we see that we don't need to consider this segment, so we have R over here. And so because they point at the same value, then our answer is just 8. So now in terms of the complexity, what's the complexity of this? Like, what do you guys think the complexity will be? Yeah, because it's like the same idea as before. Essentially, we're just cutting the array in half over and over again. And so how many cuts can we make? We can only make so many cuts, right? Because we're going to keep shrinking it by like half. So in total, we're going to make around O of log n cuts. So that's our total complexity, which is much better than our original O of n. So yeah. This is actually why sets are log n insertion and deleting. They don't actually directly store it in an array. They use like a more advanced data structure that I won't get into. But yeah, it's basically like this idea of like discarding half of the array and looking at the other half. And it's also why sets are always sorted, which is what makes it fast because of this. So yeah. Wait, have you guys heard of sets before? You guys have like heard of C++ sets, right? Oh, okay. I think I think I explained this in the first lecture, but a lot of you guys weren't here, so I can quickly go over them again. Yeah, yeah, yeah. Sorry, this is gonna be a review for you, but just for the other students. So basically sets. Um, the syntax is basically like this. So you have like set of some type value. I'm gonna use int, and you use these angle brackets. Like it's like shift comma shift period on your keyboard, and then the name of the set. And what the set does is it allows you to do like s dot insert and erase quickly. And the reason why it's able to do things quickly like that is because it always makes sure the set is sorted. So then when you insert it, you can actually just do a binary search to find the position where it would go. Now the issue is that if I were to insert something here, all these values over here have to move. So that's why it's not actually stored as an array. It's like a different, more advanced data structure. How does it ensure sorting? So the way it ensures sorting is it inserts at the value where it should go if it was sorted. So like with this example, wait, this is like really messy. 1 second. Wait. Okay. So if we had like 1, 2, 3, 5, right? And we wanted to insert 4, it just makes sure it inserts 4 here. And how does it know where to put the 4? It uses basically the same idea as binary search to find like this position. So it looks at the middle value, it discards this, and so on. Yeah. Now the reason why vectors can't do this is because notice how to actually insert it here, we still have to like move all of the values at the end back one spot, right? And if we just keep inserting at the front, that means all of our nodes or all of our values are gonna have to go backwards. So the way set handles this is they use like a different data structure, which is like pretty advanced, and I won't go over it. It's like something called a binary search tree, if you guys have heard of it. But yeah, I won't be going over it because it's like pretty advanced. But all you need to know that set has log and insertion and deletion. And also that all values will always be unique. So like for example, if we look at this again, like if we had 1, 2, 3, 5, if I inserted another 5, it wouldn't add it because there's already a 5 here. So what that means is that like it's good for like finding values, like if we've already encountered a value before. So yeah, you can look at the first lecture or like the slides for at least, and then you'll get a better idea of it. So yeah. Alright, so binary search. We always choose the middle value and compare it to the middle value. If it's larger than if x is larger than all the values less than the middle one can be discarded. Like don't need to be checked. So yeah. Yeah. Okay. So like I said, different data structures use this idea. So yeah, like I said, sets are the reason why sets are fast is because they use this idea. Maps, if you don't know what a map is, like in Python, it's basically just a dictionary, except all the values are sorted by the key value. So yeah, the implementation is a bit wonky because there's like off by ones. Because the example I showed you was really nice because each time there was a middle value. but sometimes the number of values could be even, right? So then things get a little bit weird. So I won't be going over like a specific implementation here, but you can just search online and there's a lot of good ones that you can find. But yeah, just something to be careful of. And then, so far we've actually we binary searched on an array, right, to check to find the value. What we can actually do is we can use binary search on the answer to see if certain conditions are met. And I have an example here of that actually, which I'll send in chat for you guys to look at. That's the wrong link. Wait. One second. Yeah, the second one. So I'll give you guys a couple minutes to think about it. And then after this problem, we'll take a break before we move on. Again, don't be scared that it's a silver problem. Can we find the total number of minutes and divide by k to get t? Wait. Wait, t's part of the input. They like give you t max. Yeah, also, if you guys could join this other meet, because this one's gonna end soon, so. So do you guys get the problem statement? Oh yeah, by the way, this problem is actually pretty hard, so I recommend you guys like think of like getting subtasks or like at least part of the problem. Some sort of complete search. Uh, could you elaborate on that? Because the thing is, at each time the because yeah, the cows are like not an entire set of k are changing. It's just one is changing at a time. Or like more, but like yeah. So it's not like a whole new set of k cows. I think a couple more minutes and then I'll get into the explanation. My hint is binary search. But binary search on what? Uh, okay, yeah, I think I'll go over the problem now. Okay, so um like I said, what we can actually do is we can binary search on the answer. So how do we binary search on the answer? So there's some conditions we have to satisfy first of all to know whether or not we can even like try to binary search on the answer. So the sorry, the first thing to notice is that the wait one second. Yeah, so the first thing to notice is that if we have some k that will fit within T max, then we know that all values with k that are greater will also fit within T max, right? right? Because if we have more cows on the stage at once, then it's only going to take less time, right? So in other words, as k increases, the time it takes will, for like the entire performance, will go down. Does this make sense? Do you guys like understand why this is true? Kind of like get a confirmation. Okay. Yeah. So this isn't necessary, but like a way to visualize this is actually just a graph. If this is k, this is t. So as k increases, t is going to decrease. And it might not be linear, but we know it's going to always be decreasing. And this is very, very important for binary search, right? Because like, for example, when in our array, we had to make sure the array was actually sorted first. So here, we also have to make sure that this is always decreasing or always increasing. It doesn't matter like by how much, but as long as it's increasing, it's fine. Okay, cool. So what we can end up doing is we can actually binary search on k. So first of all, let's say we know like some k value, right? And we want to test if that k value is going to fit within Tmax. How would we do that? How do you guys think we'd do that? Yeah, simulate, but with a bit of optimization. Not really optimization, but we just use a data structure to make it faster. The set to be specific. Which like, yeah, I like talked about a couple minutes ago. So let's have a specific example, right? So let's use sample here. What's the actual answer? 4? Okay. Let's use k is equal to, let's use k is equal to 3, right? So, first of all, we sort these values, right? Wait, sorry, no, we don't sort them. So basically, we maintain a set, and we make sure the set is always of size k. So what we do is, we insert the time that each cow is going to, like, each cow is going to end their thing. Like finish their performance or their dance on stage, right? So first we see 4. So the set is empty. So like our stage is empty, so we can add 4. 7, the stage is also, we still have space on stage, right? And so the first interesting thing happens when we encounter this 6, right? So this 6 will be added into our set once the minimum one ends, right? So once the cow whose duration is 4 ends, right? And it's going to take 6 minutes. So that means in total, it's going to take the minimum plus its own duration to get for its own ending time. So for example, this cow at 6, it's going to take, its performance is going to end at time t equals to 10. So our set, we can erase the 4 from our set and instead insert our 10 from the set to represent this cow. And so we also make sure that our set is always equal to size k, because this is like basically our stage, kind of. Do you guys get like where this 10 came from? Okay, I'm gonna assume you guys get where this 10 came from. So then the next value we look at is 4, right? So we know that the earliest time a cow is gonna get off stage is 7. So then we know that this cow is gonna get off stage at time equals to 11. So we get rid of this, and this is our new set. So then all we have to do is we just have to make sure the maximum time, like the latest time some cow gets off, is less than or equal to T max. And if this is satisfied, we know this K works. In this case, 11 is not less than 8, so we know that this does not work. So do you get how we check if some certain K works or not? Like, is any part confusing? Can I get like a confirmation that this does or does not make sense? Makes sense? Okay. Yeah, okay. Okay. So now we know how to check if some K works or not. So now how do we determine what K we choose? So what we can do is, like I said, we can actually binary search on this. Because remember what I said about it being like decreasing, like always decreasing, or what we call monotonically decreasing, because it's always. This is very important, right? Because we know that if some K, like for example, K equals to 5 works, then we know that K equals to like 6 to like infinity will also work, right? Does this make sense? Like if this K equals to 5 will fit within our time limit, or within like T max, then we know that K with like greater than 5 is also going to fit within T max. Does this do you guys understand this? And this is like kind of like the sorted array, right? Because we can just exploit this. So if we know if like this is T max, for example, and our initial guess is like around here, we know that all K's from here on will work. So then we can guess this K value instead. Right? And then we can just keep doing that. And for example, if some like K, if we have like some K over here, that gives us some T value that's greater than T max, we know all values less than K won't work either. So in other words, we can basically just do a binary search until our T max, until K fits within T max. And we try and find the smallest possible value by using like this binary search. Does this make sense? Like, do you guys get how we choose some K value? Or like how we try certain K values? Okay. If it does, then we can first take a quick 5-minute break, and then First I'll go over the slides and then, yeah, so a summary of what we just did basically. So if a larger value of k works, then our t will become smaller as k gets larger, right? So if a larger value of k works, that means, so if k works, then a larger value of k will also work. Yeah, so that's like basically our requirement for binary search. It has to be either always increasing or always decreasing. So we just binary search on the answer, which is k. So in order to check if some k works, we can essentially just simulate it, and use a set to find like the minimum time a cow will finish their performance, so we know when the next cow can get on. Yeah. Okay. Yeah, so first let's take a 5-minute break. And then, yeah, I'll get back to teaching greedy algorithms. Yeah. So, any observations or ideas? Yeah, first of all, does the problem statement make sense? Because this one's a little bit weird. Do you guys have like any ideas on how you would approach this problem? Yeah, I think I'll probably just go over it really quickly. So first of all, the problem statement. It's a bit weird. You guys get the problem statement at least, right? I'm gonna assume you guys do. So then, so first of all, we notice that all the values have to be even, right? Because if we're gonna get back to our beginning position, that means each time we go to the right of it, we're gonna have to come back to the left of it. Which means that all these values have to be even, right? So what we can actually do is we can greedily do this. So basically, imagine we start over here, and if we go all the way to the far right, then we can just try, what we can try and do is clear all of them in like one sweep on the way back. And by clear, I mean like reduce it down to 0, because like each time going across reduces it by 1. So it'd be like 1, 3, 3. So the way we can actually do that is, for example, this 3, all we have to do is just keep bouncing back and forth. And we make sure we end on the left side of it, which is guaranteed because this number is going to be odd, because initially it's even, and then we crossed it once to get to this side, so it's going to be odd. So because we start on this side and it's odd, the number of times like we bounce back and forth, we know we're going to end on the other side. Right, so now this value is done, right? So now we can just discard this, and then again we can just bounce back and forth until the number of times that we need to, right? So again we can discard this, and so now we just have this 1 here, and then we just bounce here, and that's it. So this gets reduced to 0. Does this make sense? Like the solution? Can I get a confirmation again? Like does like is any part unclear about like how you would do this problem? Okay. I'm gonna assume that you guys get it. How do you choose the greedy path again? Okay, so basically, the whole idea is we like greedily go in one direction. So okay, so first of all, we make it all the way to the right first, and so now what we have to do is we have to make it back, right? So what we do is we greedily try and make it back until we are forced to go the other direction. And what do I mean by forced to go to the other direction? Like, for example, if it's greater than 1, then we know we have to go backwards, right? Oh, wait, did I? Wait, one sec. Uh, oh, wait, sorry, wait, I think I did this wrong. Wait, one second. Hold on. Huh. Okay, wait, yeah, wait. Wait, no, okay, wait, I think, sorry, wait, I said this completely wrong. Okay. Yeah, okay. Sorry, so the greedy here is basically, what we do is we just keep greedily going in one direction until we're forced to change. That stays the same. But how do we know when we're forced to change, right? Basically, we're forced to change if, as we go, the value before it is like, okay, wait, how do I explain this? So we're forced to go backwards if the previous value is like still greater than 1. Or still greater than 0. So for example here, we initially start over here, and then we keep bouncing, we keep going to the right, and then all of these values will be reduced down, right? So then once we're here, we do the exact same thing and we keep going until we get to a value that's like if we cross it, we can't come back, right? So once we get to over here, then we just repeat the process again. We just bounce back over here. So this gets reduced down to 2. And once we're here, then we keep bouncing back again. Does this make sense? Okay, wait, this is kind of scuffed. Okay, so like, yeah, so like basically like, the idea is that we just like keep going in one direction, and then we'll go in the other direction if we have to. And what counts as if we have to? Well, if there's like, if the value, if like we're going backwards, if these values here are still greater than 0, we're going to have to go back to the right. And we're going to keep going back to the left until we reach a value that's like, until we reach a 1, basically. Because once we go past to the left of 1, there's no going back, right, to the right side of 1. So we have to make sure this entire segment over here is done first. And then after that, we just keep going left. And so on. So does this make sense? Sorry, the beginning was a bit weird. I think I read the problem wrong, I guess. But like, does this algorithm make sense? Okay. Okay. I'll change my slides because I think my slides also. Yeah, okay. I'll change my slides later and then, oh, yeah. And then the next problem. Here. So do you guys have any ideas? Okay. Um, I think I'll go over this problem really quickly. So, because the meet's about to end. So, um, do you guys get the problem statement? Basically, Bessie wants to run um, at least k meters. Okay, so basically, Bessie starts off at a speed of 1. And at each time frame, she can either increase her speed by 1, decrease her speed by 1, or stay the same. So then the question is that basically we have some value x where Bessie wants to finish a k meter race within where she ends the race with speed at most x. And then and then we have to find this value for x from 1 all the way to n. Does that make sense? Like the problem statement? Yeah, okay. So the way we do this, so like intuitively, the fastest way we can, like, if you want to finish the race as fast as possible, right? Because she wants to finish it while staying under the limit at the end. So intuitively, basically what we're gonna do is her speed is gonna look something like this, where she's like increasing her speed, and then we're gonna hit like a cap where she can't increase anymore. Because if she does, then she won't have enough time to go back down, right? And then she spends the rest of the time going back down to some certain speed, right? So then, what we can actually do is we can simulate each second of the race. And you can actually prove it. I won't prove it right now, but it's around like 60k, I think. The time, like the total number of seconds in the race. So first of all, let's think about if I have some distance d left, right? So let's say this is our track. I'm over here. We have distance d left. And currently I'm at speed s, right? And our goal is to end with speed x. How would we find if we can do this in time? Assuming there's d distance left and our current speed is s. Well, we know that the total distance traveled in that time when it's decreasing is just equal to s plus s minus 1 plus s minus 2 and so on, right? All the way until x, right? This is the total amount of distance we're going to travel during the time frame where we're trying to slow down. Does this make sense? Like where this came from? Because at the first second, her speed is this. During the second, her speed is s minus 1. During the third second, her speed is s minus 2, and so on. Right? So then, essentially, what we can do is we just... Yeah, exactly. Well, actually... Yeah. To be more accurate, actually, you only need, the distance that you need is actually this all the way to x plus 1 instead of x. And then plus 1, because you only need 1 meter to actually like slow down, right? Or like 1 second to actually slow down to x. So you can be like at like this part, like let's say there's only 1 meter left. You can get down to x plus 1 by the end of this, and then spend your last second getting down to x. So it's actually this. But yeah, basically what you said. This is essentially just prefix sums, like I explained once upon a time. So this is just the sum of 1 all the way to s minus the sum of 1 all the way to x, right? And we know this is just equal to x times x plus 1 over 2. And we know that this is s times s plus 1 over 2, right? So we just have to make sure that this difference is like less than or equal to d. And then we'll be fine. Or like using this instead. So this would be like x plus 1. And then, yeah. Oh no, sorry, yeah, it would be x because this is x plus 1, so. But yeah, that's like the basic idea of it. And then, so for our actual simulation, it's very simple, right? Once we have this check, like let's say this is a check function, then at time t, all we have to do is if check of distance plus s plus 1, and then s plus 1, if this works, sorry, this should be distance minus s plus 1, and then x. So if this works, that means essentially we can increment our speed. If this doesn't work, then what we try is we try staying at the same speed. So d minus s, and then s, and then x. This is essentially staying at the same speed. If this doesn't work, then that means we have to decrement our speed. So yeah, basically the greedy here is we're just trying to go as fast as we possibly can until we're like forced to go slower. So does this make sense? Okay. So yeah, if you guys don't have any other questions, then you guys are free to go. Today's class was pretty long. So yeah. But yeah, the slideshow basically just explains this in more detail. So yeah, you guys are free to go now. If you guys have any other questions, you can stay and ask. All right, bye-bye.